Yeah. So
sorry, does anyone know where Roman is? I noticed he's not.
Oh,
here.
yeah, good question.
Oh, should I wait another minute for everyone to?
I guess so.
Okay. Or I mean, I can begin with general. I don't know. I'm Sam Eisenstadt. I'm a research fellow at the Machine Intelligence Research Institute. Yeah, I'm going to talk about Bayesian epistemology and Garrabrant induction. Does this look good?
Oh,
Am I right even bigger, or just give up on the whiteboard and go back to the slides?
I'll pin you. Okay.
Yeah, also in me. That's a good idea. And yeah, I hear you've been looking at Garrabrant induction. So I'll try to write large math symbols. I can also change the slides if it's not working. Yeah, so the idea, I don't know, is everyone here? Should I go ahead?
I just messaged Roman, so if he gets on Discord, he will be reminded.
But maybe I should just start.
I don't know what's happening. Yeah.
I mean, it's being recorded, so.
Oh yeah, right.
Yeah, so we want to compare these two ideas of like you have your Bayesian epistemic subject and Garrabrant inductors, and so I guess what we're gonna ask is like what survives and what has to be changed. So there's sort of two aspects to this. So one thing I want to say is that I think like Garrabrant inductors are like good at doing a lot of what we want, what we expect from Bayesian epistemology. And so we can consider a lot of ways that we use the idea of Bayesian agents. So yeah, I mean, we'll have like statistical learning. There's the merging of opinions theorem. So these aren't all things I'm going to discuss, though I can go into them if they're...
What is the first word there? What of opinions?
Merging.
Yeah, I
assume.
Oh.
There we go.
Yeah. So this is a theorem that says sort of it's this idea if you have two different priors and you update them on the same sequence of evidence, then they converge with each other in terms of the probabilities that they predict for the next observation. So I don't know how familiar people are with this, but I think it's a nice, it's sort of like an objectivity of Bayesianism kind of result. And I mean that's not stating the whole thing. There are hypotheses about like how the priors have to be. But we get this idea that like even though we start out believing different things, we come to make the same predictions because we're observing the same environment. Oh, someone's raised a hand.
Yeah, that's me.
Yeah, do Do we want to manage this somehow, or like I don't know. I might not pay attention, so maybe like one person should.
Yes, that was me.
That's you.
Yes.
Yeah. Well, so I see. Yeah, you're the. Well, if you're the okay. Yeah, maybe I'll just keep an eye on this. Yeah. So what's your question?
Yeah, I was going to ask what's the relationship between merging of opinions and Allman's agreement theorem? Is this like the off equilibrium version of the off equilibrium slash how do we end up at equilibrium sort of thing, or is there some other detail I'm missing here?
Yeah. So the merging of opinions theorem does not assume common priors. So
Right. And Allman's agreement theorem is if you start with common priors and you see the same things, then you end up in the same place. And this is even if you start with different priors and you see the same things, you'll get towards the same place. Yeah.
yeah, I mean, Auman's agreement theorem has a different idea in it, which you could put these two ideas together. Probably you could have some sort of like Aumann agreement / merging opinions combined idea.
I'm missing that.
And the idea of Aumann's agreement theorem, we don't assume that the agents are making the same observations. We only assume that they have common knowledge of each other's beliefs. So I might not know
Okay.
everything you know.
I see. So this is the complement to Allman's agreement theorem, which is like Allman's agreement theorem is same prior, same update rule, see different things, you'll end up at the same place anyway. This is different priors, same update rule, same new evidence, and you'll still end up in the same place.
Yeah, it's different priors. Like I mean, it's Bayesian updating, so you can say they're making the same update rule, but
yes,
we have the same evidence, but from different priors.
Yes.
So, yeah.
Okay.
What's the name of the agreement theorem? Sorry.
Aumann, A-U-M-A-N-N.
Oh,
yeah,
okay,
I can. I mean, that's also. I'll write that also. Yeah, I think it's a little disappointing that Aumann's agreement theorem gets all the attention, and I don't know. To me, merging of opinions is a major result, but
it seems like a major result, but I can at least see why Aumann's agreement theorem gets all the press, because like this one merging of opinions seems way more. Obvious on the face of it isn't the right word, but like way more intuitive, way more what you would expect, because you could say as long as you don't have trapped priors of some weird kind, then yeah, of course as two agents see a billion times more information than was ever contained in their priors, they'll wind up converging to the same thing if they have the same update rule. Whereas Allmann's agreement theorem, now that I remember the actual form of it, is a little bit more surprising because sure, you started off in the same place, but then you went off to see different things. You shouldn't necessarily a priori believe that you end up in the same place anyway.
Yeah. Yeah, and so like in the Garrabrant induction context, I think like we can't quite say these things about let's give these two Garrabrant inductors common priors. And so I think we can't really pose like a pure Aumann agreement analog. We can maybe have in some form. I mean, yeah, we could have something that I would say should count as logical inductors with common knowledge of each other's beliefs who have different beliefs.
Okay.
But I mean, there's not really a sense in which they have common priors. But from the sort of point of view that I want to say of Garrabrant induction really does replicate a lot of the Bayesian phenomena. I do want to say that that like we get what we want in some form, but we have to do like some combined Aumann agreement merging of opinions theorem rather than the pure Aumann agreement theorem. And so, yeah, so I have a few other, so I mean, there's other things we might want to do in Bayesian epistemology. We might be interested, and this comes from the history of the Aumann theorem and game theory. But we have this idea of like hierarchies of meta knowledge. And so, you might think of like the blue-eyed islander problem, And so you can try to do that in a Gauss-Branch induction context. And more generally, you can try to do game theory. You can have different Gauss-Branch induction agents playing some game against each other. You could ask that they replicate Nash equilibria or correlated equilibria or something. And so I think all these kind of Bayesian stories, we can tell some kind of Gauss-Branch induction story. And so I'll give a I'll give an example of this, a pretty simple one, but just to sort of give something that's easy to state, but indicates like how these kind of things can change. And so this, I mean, in a logical induction context, I mean, it's one of the simpler properties to prove. But there's a theorem in probability theory that's the Doob martingale inequality. And so I'm going to state this and give a proof maybe. So let xn be a martingale with xn is certainly in the interval 0, 1. And let u be the number of upcrossings of xn over the subinterval AB, which is the subinterval of 0 or 1. Then the expected value of u is less than or equal to 1 minus a over b minus a. So I think we can even get a tighter band. I don't know. Maybe this is the tightest band. Yeah. So what does this mean? So should I explain all this martingale? Yeah. So
Can you also write the name of the theorem on the whiteboard?
Oh, yeah, I thought I did, but yeah. So that might be a little cramped. Should I write the name larger?
DOOB?
Yeah, DOOB. Yeah, I'll write Doob larger. Let's use the...
I just want to make sure that we don't like massively run over time talking about things that I guess I'm not entirely sure how this connects up to any of your other topics, or
the
fine details this are what we need.
That's right.
I'd be happy to talk about this indefinitely, but that's kind of my one major weakness as a facilitator, which is that I'm happy to go down whatever mathematical rabbit hole.
Yeah, that's a good suggestion. Yeah. So I mean, just to say very quickly, I mean, like a martingale, I mean, we have this conservation of expected evidence idea that, we're as likely to move up as to move down in mean. And so the number of upcrossings, so it's like I have this sort of random walk, and then I can look at the number of times we're below some point and then above, like we're below A and then above B. And this can be bounded. Maybe I shouldn't sketch the proof. But I mean, the conclusion is that the expected number of upcrossings is small. So.
Sorry, what's an upcrossing?
An upcrossing, it's the number of times that you're below A and then later on you're above B.
Okay, so an upcrossing is always with respect to some open interval?
Yes. Yes, the upcrossing's over some interval.
Ah, I see. Got it. So is there a reason why we don't mark U as dependent on that? Or yeah, is there a reason why we don't mark U as being dependent on that in the notation, or is this just for brevity?
I said let U be the number of upcrossings over AB. Just
Sure.
Yeah, we could. Yeah, so sort of the point here. I mean, we can compare this to some logical induction version. You know.
Just to make sure that I've understood what's going on with upcrossings, because it's a little bit unclear there. If we have some if we're looking at the number of upcrossings from from the number of upcrossings over say 0.4 to 0.6, and we go 0 to 1 to 0 to 1, is that 2 upcrossings or is it 3?
That is 2 upcrossings. Yeah,
Okay,
the crossings in the upward direction. But also, if you have 0.51, that's also an upcrossing. So it has to be below and has to later be above. But it could.
Yes. Now I'm mostly asking because you could look at. I mean, depending on the way that you define subsequences, you could be looking at. Oh, okay. Well, over this entire subsequence, it jostles around a bunch of there. It wasn't clear that there was an additional monotonicity condition there.
Initial what condition?
Monotonicity of like.
Monotonicity.
You can't count the larger interval as, oh, well, on the left of this interval, we were at 0.
Yeah, yeah,
sorry, the left of this sequence, we were at 0. On the right, we were at 1. So maybe this should count as another larger upcrossing that contains the other 2. But I see what you mean now. Yes.
Yeah, yeah.
Norman, did you have a question?
It's like the number of consecutive disjoint.
Norman, you had a question? You're muted right now. Is it in the chat?
No. Why do you think I have a question? Sorry,
You were
sorry,
waving a lot.
I was picturing the upcrossing. Sorry about that.
Yeah. So well.
But it's not a monotonicity condition, though. So you could totally do this non-monotonically. Huh.
Yeah, so then we can have a version of the Doob-Martin inequality for Garrabrant induction. And so this would be something like this. So you have some belief sequence Pn that satisfies, let's say, some effective Garrabrant induction criterion. So what do I mean by that? I mean, like, for each trader, we have, explicitly some. We have some function that tells you the some bound that the trader can never do better than. Then there exists a bound on the number of upcrossings of the probability of phi over AB that's like a function of phi AB.
So what is GIC there? I assume that's Garrabrant induction criteria? What was the first word? Okay, it is Garrabrant. Got it. Can you explain what that is? Because I don't even know what we're doing here.
I mean, this is the. I mean, the familiar. The Garrabrant induction criterion that, like, for every trader, it's like if its wealth doesn't go to minus infinity, then its wealth also doesn't go to infinity.
So Garrabrant induction is synonymous to logical induction in your usage. Okay.
Yes.
Okay. So is this just saying that the number of upcrossings is finite, or is there like something stronger than that?
Sorry, it's a little hard to hear you. It's saying that no trader exploits the market.
Is this just saying that the number of upcrossings is finite, or there's some stronger claim?
Yeah, it's saying the number of up crossings, you know, there exists some it's like I'm saying the number of up crossings is bounded by like some explicit function of the sort of like, I mean, if we like, for example, we can satisfy the Garrabrant induction criterion with explicit bounds in terms of some kind of measure of complexity of traders. And for any such function, we get some explicit function of phi A, B that gives some corresponding bound of the number of up crossings. And so sort of the point I'm making is that, like, in the probabilistic world, we could have infinite up crossings, but with like smaller and smaller probability of having, it's like we can't have like large probability of having more than some given number of up crossings, some explicit thing. And this in a sense is even stronger. It's like we certainly can't have more than some bound of the number of up crossings.
And so hold on. So is that bound known to always be finite, or are there some cases, some choices of phi or A or B or some combination of all three, such that that bound is actually there is no bound?
No, so it's some finite number for every, because I mean the point is there's some trader that does it. There's some, it's like if you give me a bound on the wealth of this trader that like waits for it to be below A and buys and waits for it to be above B and sells, and you have to make this soft so that you deal with the continuity. But this actually enforces that this can't happen more than some number of times, that some explicit function of of these parameters based on how the how the Garrabrant induction criterion bound is a function of the trader.
Maybe this is a little bit out of scope, but I'm thinking about propositions phi that maybe depend on the day number. Is that something that's allowed or no? I assume not, if they're saying.
Well, so it's a function of phi A and B. So if we consider some sequence of different propositions phi, it might be that this bound gets worse and worse, varying phi. But it's like for each particular phi A and B, the number of up crossings, you can give some explicit bound.
I think I might not have been fully understood there. I'm saying that there is a single phi whose truth value depends on the day, and I assume that this is not something that's allowed. Like something like today is an even count day.
A single phi can't, its truth value can't depend on the day. We would have to move to a sequence of phi's in order for the truth value to itself to, of course, the price depends on the day.
Yeah. Yeah, I wasn't sure. And hold on. So the other thing I'm just trying to figure out what the additional constraints are here that aren't quite written down. And then the other question was, and this should still hold for no matter what observations this market sees.
Yeah. I mean, this is all.
Because now I'm just thinking about a good example where you have some phi.
The introduction criterion is relative to like the evidence sequence, or what's called, I guess, the deductive process in the paper. But it's like the evidence sequence. Yeah, I mean, it's it has to eventually have every theorem, and it can also have whatever empirical facts. And this is all part of the Garrabrant induction criterion. So it's like if we put in some randomness in there, like maybe the observations are somehow being treated as random. This doesn't care about that. It's like that can just.
No, I'm not thinking about random in this case. I'm thinking about we have some perfectly normal proposition phi, like, I don't know, the weight of this melon is exactly 5 kilograms, and the evidence that this market gets is badly formed or adversarially chosen in some way, such that the estimate on whether that is the weight keeps yo-yoing up and down forever, because one day you get fed actually it should be more than this, and the next day actually it should be less than that. And because of the evidence that you're getting, the actual legit price estimate on that proposition just keeps bouncing up and down forever, specifically because of the kinds of evidence that get fed in.
Yeah, so I'm saying
Happen, or-
specifically that we shouldn't expect that to happen. That's epistemically we shouldn't think like a good agent would update their beliefs that way.
No.
And I think
Well,
the logical induction argument is like a good, like if you think about why it works, you maybe come to understand why a good agent shouldn't think that way.
I'm not saying that a good agent should think that way. I'm saying, what about the case where there's some really, really adversarially cooked up evidence stream,
Then
such that
you've broken the logical induction criterion or the Garbrand induction criterion. Like, yeah, like the theorem is saying this can't happen.
Yeah, like if you think about like the logical induction algorithm, like basically there's this trader that's like, oh, we keep having these upcrossings. Maybe I should be suspicious about this counter evidence. Maybe it's adversarially chosen, and I should, if I keep going, I should expect I'm going to mean revert, and it prevents you from actually doing that.
okay, that makes sense.
Like I come to see the pattern. So yeah, so let's get to the other. Yeah, I mean,
Is there an exact form of? Sorry, one last question about this before we move on. Is there an exact form of that bound known, or is it just we know some bound exists?
Yeah, you can make this explicit.
Okay.
So yeah, so I want also to say that we can ask for something stronger. We can ask not just does do Garibrandt inductors resemble Bayesians, in that we can do all these kinds of things that we expect from Bayesians. We have these martingale properties, this game theory merging of opinions, etc. But we're also we can ask if they resemble Bayesian subjects in an even stronger sense, which I can say something about. So, I mean, we can sort of put Garibrandt induction and Bayesian induction into a common framework. So it's like we have some language L, we have some evidence sequence D, and we have our belief sequence P. And so we can think of the content of Bayesian epistemology, or, well, yeah, I mean, we can think of the content of the update rule at least. We say that by definition, the probability of a sentence tomorrow is the conditionalization of the probability today on the evidence tomorrow. And so, whereas Garibrandt induction, by contrast, says something much more general. It's just saying the belief sequence is some belief sequence that satisfies this overall criterion from day to day, but it's not giving this like narrow update rule of this is how the beliefs tomorrow have to be derived from the beliefs today. And we might think like there isn't some function of the beliefs today that give the beliefs tomorrow, but it's just some overall coherence, or we might have like the construction in the paper, some algorithm that keeps track of some auxiliary information beyond the beliefs about the sentences today. And I mean, technically, this is also true of Bayesian induction if we let things be continuous, but it's undefined on a set of measure zero, but that's not so important here. So yeah, so So then we can ask, is this really secretly a Bayesian agent in some sense? In this common framework, can I say, like, actually what we should be doing from day to day is updating on some sentence and thus forming tomorrow's beliefs. So I think there's some reasons that this is desirable and some reasons that this is undesirable. It's desirable because it sort of explains the change. It's like, not just like, well, these are the beliefs the next day, and somehow this works, but we're like, if I could write down some sentence such that tomorrow's beliefs were today's beliefs conditioned on the sentence, then we think we have more understanding of what's going on. But also, I think it's undesirable because I think that there's something sort of wrong with the update rule. And yeah, the Bayesian, they sort of have all the hypotheses in their prior from the beginning. And so, but there's all these reasons that you shouldn't be able to have all the hypotheses from the beginning. Most simply, you can just say, like, well, this isn't a what do you call it? This isn't a requirement of rational agency. People try to give these Dutch book arguments. If tomorrow's belief is not this function of today's belief, then I can Dutch book you, because I can say, it's like for every possible observation, I know what you'll believe tomorrow. And so if it's not the conditional today, I can make this conditional bet with you today, and I can make the opposite bet with you tomorrow, and I get a sure profit. And Abram has written about this connecting it to Jeffrey's idea of radical probabilism. But I think this Dutch book argument is sort of assuming too much. That it's assuming that for every possible observation, it's like you can actually, like, think through, oh, here are all the possible observations tomorrow. Here's what I would believe in each one. And I don't think having done that is a requirement of rational agency. It's sort of akin to the whole problem of logical uncertainty, where, you might say a priori, if something is a tautology, it's a requirement of rational agency to believe it, but we don't actually think that's reasonable. In fact, there's no algorithm that looks at the sentence and tells you whether it's a tautology. And so then another way to think about this sort of thing is with diagonalization, self-reference, where, we can have these kind of hypotheses, which is sort of what's
Just a moment. Yeah, we have a question from Norman. Could you go ahead?
Yes, thank you. So I'm a bit unclear about the goal here, because so we have logical inductor construction already, and are we trying to improve on this construction itself, or are we trying to find an update rule that makes the pattern by which the logical inductor updates the probabilities be interpreted as some kind of marginalization on evidence?
Yeah, that's yeah, we could be interested in either of these, I guess, if I've interpreted your questions correctly, because I think sort of the most general, like, if we could give any any like prior and you know evidence sequence that such that the consecutive conditionalization satisfied the Garrabrant induction criterion, then that would be of interest. That would be well, I'll maybe it wouldn't be of interest, but I mean a priori it might be of interest, which I'll get to think more about that. But yeah, I mean it might be that we have a method that takes like some particular algorithm and produces exactly the beliefs produced by that algorithm. But more generally, like, you know, it's hard to, like, we really only have approximately one way of satisfying the Garrabrant induction criterion, which is by some sort of market process. And, you know, you could add some modification. You could do the market process a bit differently, or you could add something on top of it. But it's like, you know, either, you know, we'd need like a really different construction, or like we need the market process to somehow be the same as conditionalization.
Okay,
Just,
so
Go ahead.
oh no, it's okay, Paul. Okay, so it's like we're trying to do Bayesian updating and make the results as good as the logical inductor as possible. Can I interpret it this way?
Yeah, that's yeah, I mean, I'm not sure. I mean, yeah, that's the. I mean, I'm sort of now giving reasons that maybe we don't want to do this, but yeah, it's the question: can we do this? And like, if we could do this, that would be interesting. So yeah.
For my part, just a quick question. Can you give
Sure.
us like a motivating prose version of the Garrabrant or logical induction criteria? Because like we can go and dig up the actual math to it, but that doesn't necessarily give us a strong idea of the significance.
Okay,
wanna
yeah,
get,
maybe I'm assuming too much here. So yeah, I can overview it.
Let me like dig this up again to make sure that it's not as like it's not just really straightforward and I'm missing something, because that's entirely possible. That's definitely a possibility.
Yeah.
Oh.
So the
Oh, I see. It's just the one thing. It's criterion singular, right? Or no?
yes, yeah. I mean, it involves like a quantification over traders.
Huh.
But yeah, I mean, we think of it as one.
It's a trader that's not Dutch bookable.
All the traders together.
It exploits this relative to the deduction process.
And so, yeah, I mean, it's you know, to say that it's like you know, for all traders.
Okay, I'm a little surprised then.
It's like if the, I mean, yeah, you for the full version, I don't have like the statement written down. It's like if the wealth is bounded below in all possible worlds at all times, then it's also bounded above. And so this, I mean, you have this idea of where what the space of possible worlds is changing over time based on the evidence sequence. And so you can look at the full formal version of this. But basically, yeah, I mean, it says you can't be exploited by any trader. But the idea is like every trader is some kind of like Dutch book-like sort of provocation where it's like you have this this property that it's like you should be able to arrange your beliefs so as not to be exploited by. I mean, it's like you're an efficient market against this trader. I don't know how well that.
Okay, I guess I was expecting a much more. I must have missed this when my first read through then, because I had been expecting a much more granular condition in terms of the traders, not in terms of this market as a whole has this property. Although I guess it's probably the right level to think on.
The like there's the distinction between the logical induction criterion and the logical induction algorithm. The criterion is like this very general thing about some sequence of beliefs.
Okay. Dr.
Yeah. I think this is something I would want to stress, that like, I mean, you should think of Garibaldi induction as being like the Garibaldi induction criterion. It's like this is like our
Okay.
criterion of rationality. And then, I mean, the algorithm is also interesting. I think mainly for the
Yes.
existence property, but more generally for like thinking about the. I mean, the traders are both used in the construction and in the criterion.
So this is like so this isn't like we're assuming that this has a specific form. This is just a very I don't know if I would say weak, but it's a fairly weak regularity condition on there's no way for any of these traders to exploit this market in like there's I'm thinking partially about the backside of this, which is that there's no trader in this market that's acting in an exploitable way. But is that just the same thing?
No, because the traders are trying to exploit the market. So it's like the
Yes.
prices are not exploitable. But the prices, I mean, in the construction and the algorithm, the prices come from an equilibrium of the traders.
Yes.
But on the level of the logical induction criterion, it's just that the prices are not exploitable as a whole. There's no strategy that makes an infinite amount of money without risking an infinite amount of money.
Okay, got it. Lauren? Lauren has a question?
No, I'm just pointing out that several of us in the chat would like to see the main results and not.
Sorry, yes, go ahead.
Yes. Yeah. So I guess. Yeah. So the idea. I mean, we basically we can do this. We can produce some prior and some evidence sequence, such that updating on that evidence sequence. So, yeah, let's and I mean even a even a computable prior. Yeah, there exists a computable function from the language to 0, 1, I guess. Well, a computable sequence, so it's also computable in N. No, sorry. It's not a sequence. That's the point. It's a prior. It's a computable prior, which so this so it is a probability. Well, it's a probability distribution in the sense of propositionally consistent worlds. Or, just in the sense of propositional consistency. Such that, and there's an evidence sequence Bn such that Pn equals P conditional on Bn is satisfied. Is a Garibaldi inductor. So satisfies. And so, so what evidence? I mean, there's two evidence sequences here. There's the there's the Bayesian evidence sequence that I'm conditioning on, and there's like the Garibaldi induction evidence sequence that's implicit in the Garibaldi induction criterion. And so it's like, I mean, so it's I mean, basically there's like some function. So, well, I mean the simplest version, I mean, you can think like the paper, where like the evidence sequence is itself deterministic. I mean, we might want to we can strengthen. I mean, it's nice to have this as an explicit function, because then like we can have the evidence sequence belonging to the Garibrandt induction criterion vary. We can say like, well, you can make these different observations, and so you get like a tree of possible ways that things could unfold. And then it's like the conditioning with respect to Dn is always going to satisfy the Garibrandt induction criterion for d tilde n for like a family of evidence sequences d tilde n.
I think I've missed something here. So you're saying that there's a bunch of different evidence sequences, like there's an entire family of different evidence sequences that all give you the same PN here?
No, each d tilde n gives you a different dn. So I mean, the point, like, if we just had logic, then there would only be one dn. I mean, we could consider like varying the order in which like logical sentences were revealed or something.
Okay.
Or like how many are revealed at once. But more generally, like, I mean, we could have like empirical facts, and we could have like multiple d tilde n's because they like reveal different empirical facts. You know, I open my eyes and see blue, or I open my eyes and see red. And then they're going to be different dn.
Then I think I've missed what it is your function f is doing there. I must have been writing something down at the time. What is that f doing?
Well, I mean, it's gonna. I'm gonna construct it, but the point I want to distinguish, like, when I say there is an evidence sequence dn.
Okay.
Yeah. What do I really? I mean, I want to say there's one pn that simultaneously, like, the conditioning on dn satisfies the Garibrandt induction criterion for all these different d tilde n. By it's like for each d tilde n, there's some corresponding dn, such that the logical induction criterion for d tilde n is satisfied by Bayesian conditioning with dn. So I mean, the function, I don't know, like I could express this better with quantifier ordering or something, but
all right.
But the point is like one.
So yeah, so Sam, can I? So you're basically saying that for any like Garibrandt inductor in full generality, you can just like write down a prior that would such that updating this prior would satisfy the Garibrandt induction condition, but for this you need to apply some clever transformation to the evidence. Is that what you're saying? Like you're not just updating by the evidence, but you're updating by something more complicated?
Yeah, that's right. Yeah, I mean, I should say a bit more, like, you don't want to just update on the evidence. I mean, in general, like, I mean, yeah, Abram wrote something about our work on the this untrollable mathematician problem that gives some context for this. But I mean, in general, like, if on day n I observe phi of n, I can't just condition on phi of n being true. I have to condition on I observed phi of n on day n. Or I'm going to have all these, I mean, like in general, like, well, yeah, I mean, for any prior, I can mislead it about, for a large space of priors, I can mislead them about some particular sentence by conditioning them on some other thing. So like, if you have some sentence phi, and I want to convince you that phi is unlikely, then, yeah, so it's like I want to convince you that phi is unlikely. So if I can sort of adversarially, like, just tell you any true fact, I can tell you not phi or phi and psi, where psi is chosen to be true and the probability of psi given phi is small.
Sure. So can you give some? Can you give us some sense of how this F works? How do you compute this?
How the construction of this works, you mean?
Or like specifically the F part, I think is the most maybe. I mean, all of it is interesting, but
Yeah. I think this is the. I mean, yeah, I'm running out of time, but this is what I want to do. And I do want to caution. I mean, I think this construction is actually unsatisfying. It's sort of like we do it by fiat in a way that like technically satisfies what we asked for, but in sort of this most trivial way or something, just by fiat. Yeah, so what's the idea? So I'm going to construct P in stages. So yeah, basically with like a sequence of Markov kernels, if you're familiar with that. So I'm going to give like a distribution on something, and then I'm going to give a distribution on the next part given the first part, and the next part given that, and so on. So yeah, so I mean, we start. Yeah, so it's like we write our language as this union of finite subsets. And so it's in general in the Garrabrant induction criterion, we can sort of get away with only having reasonable beliefs on a finite subset at a time, as long as these subsets are expanding enough, because any trader can only look at some finite set. So we just put the we just have to eventually get to can only look at a finite set on any day. So it's like as long as we eventually look at the sentences for any trader, then it's fine. So yeah, so what's the idea? It's like we can define P on the first part to just be, let's say we have a Garrabrant inductor Q. So we can just define it to be Q on day one. And then we're going to define so we're going to have some random variable basically Q2 which we sort of don't have to constrain at all. We could constrain it if we want to be a bit more reasonable looking, but this doesn't actually matter. And then it's like we define P on it's like we define I mean we have like our Markov kernel from like the worlds of I I guess like L1 and Q2 to the worlds of L1 and Q2 and L2, where we just have, you know, P of phi given Q2 is Q2 of phi. So what is this saying? It's like I have my beliefs on day one, and then I have my distribution on what I will believe tomorrow. And it's like for any, which I mean, if we want to make this finite, we could make like a finite discretization of Q2, and that's fine. And then it's like if I condition on Q2, that just tells me that I believe exactly as Q2 tomorrow.
Sorry, what's the symbol? Sorry, go ahead.
Yeah, and there's a consistency condition that this has to satisfy, because P phi has to be the integral over values of Q2 of P phi given Q2 times P Q2. Yeah, I mean, there's maybe I should use like quotes for this, because the point is here Q2 is a symbol in language, and here Q2 is like the actual. I mean, like this could be like a big symbol that's like a big inventory of all your beliefs, or like a string of what is this? A symbolic expression. But the point is that this is just some number of consistency conditions that I can pick by picking this. So yeah, so I'm yeah, I guess we're getting to the end of the time. I'm happy to stick around, but yeah, maybe I should allow questions about like what this construction is or about more general things.
So you mentioned this, you can discretize it, but you don't have to, right? Like this inventory of all the prices could be exact. Like just the exact like rational numbers, or maybe not even rational numbers. I don't know exactly how we're restricting this.
Yeah, what did I mean by that? In order for it to be exact, we do have to, like, the language can't be like a countable number of, I guess the language could be a countable number of sentences. We could specify, yeah, I guess, yeah, like we just have this, but then the DN would have to be continuous, right? Like we would have to condition on like the infinite number of sentences that give like the Dedekind cut of like, this is where,
yeah,
this is exactly where Q2 is. Which, is that going to break the computability of P? I would guess not, but I was thinking about the discrete version when I say this computable P.
So can you say a bit more about what the discrete version is?
Yeah, so the discrete version, yes, we have to, yeah, basically we have to pick like a big sort of grid of possible P of Q2, like of possible like Q2, such that like the grid has to be big enough that we can satisfy this integral condition. It's which, I mean, like this is like convexity, I guess. It's like we have to be able to like satisfy these linear constraints by manipulating like the probabilities, different P of Q2. And then also the discretization has to be small enough. Like we started with some belief sequence Pn that satisfied the Garrabrant induction criterion. But here, your conditional beliefs are going to be Q rather than the original Pn. So I have to like choose Q to be close to P. So I have to pick the discretization small enough that round off might make you more exploitable by a trader. It might like you change the prices slightly, so the trader might do better. But you have to pick it small enough so that it doesn't change whether the trader really exploits you or not.
Right. It doesn't mess with the criterion.
Yeah.
I have a quick question and a less quick question. The quick question is an notational one. When you're writing stuff about worlds there, what's the symbol? I can't actually quite read that sentence at all. I can't read the subscripts, and I'm not sure what the symbols between the L's and Q's are. Are those timeses or
Yeah, those are
pluses
timeses.
or tiny ampersands?
Yeah.
Okay, so these are sample
Well,
spaces.
I mean,
then. Yeah.
Well, yeah. This actually doesn't make sense. Yeah, they should be like unions, I guess.
Wait, unions rather than products?
Yeah, because they're languages. I mean, this is why I had to write like worlds of these, because like the language is a set of sentences. So
If that's the case, then surely we can just rewrite that as that right side as worlds of Q2 union L2, because we know that L1 union L2 is just L2.
yeah.
Right.
That's right.
Okay.
Yeah, I think I just forgot that I had explicitly assumed this, but yeah, it's simpler to assume that.
Language. And all of our LI are languages then?
Yeah, they're sub-languages of L in that they're subsets of the set of sentences. I mean, yeah, we might as well assume here that they're closed under propositional connectives, because I have to say this about worlds anyway. But we could consider similar. We're in some sense like not leaning too heavily on them actually being closed under propositional connectives, and they're not closed under quantification if they're finite. I mean, the point is, since they're finite, they can't be closed under like arbitrary, like. Yeah. So.
And then the less quick question. Go ahead.
Julia asks, can you give an example of an element of L?
Yeah.
Yeah. So you know, if our original language is language of arithmetic, then we could have an interesting sentence like exists n such that n squared equals 521. So this is a sentence in the language of arithmetic. And if our language also has some further non-mathematical properties, there might be P of T, where maybe P of T means that I see the color red at time T.
I think one thing that people might be missing, like Julia and other people might be missing about the language, is that language has some signature that tells you both what symbols appear in the language and generally also gives you some semantic meaning for, or can give you some semantic meaning for any atoms of the language or any symbols in the language. So like there might be a special symbol for 0, and that means this is 0. Or there might be a special symbol for observation of red, or this is a weight, that kind of thing.
Yeah, like the evidence sequence is really sort of what ties the belief sequence to any meaning that we might want to give these symbols. So, if when the agent sees red at time t, it becomes evident at time t that P of t, then we've sort of tied the symbol to this meaning of seeing red at time t. But then this is more complicated for mathematics because, presumably this is false, and we can refute it in some finite computation, but some other sentence in the language of arithmetic, we might not be able to prove or refute with any finite proof. from
Yeah.
say the Miano axioms.
Yeah, but in particular here, our dn and our d tilde of n are, I assume, sets of sentences from L or sets of sentences from maybe Ln.
Yeah, from well, I mean, yeah, from L. I mean, yeah, like I mean, here I only used ln in the construction, so.
Right, but I mean, what I'm asking is it the case that the set of sentences you get on day n is constrained somehow by language on day n? Or is
Set
that
of
not an
sentences-
assumption we make?
Yeah, what's the?
I also still wasn't totally sure
Yeah,
what was going on with
maybe
the.
I'm not sure.
Good.
The meaning of your question, just.
So we have dn, we have ln. Is dn an element of ln? Is dn a subset of ln? Is dn not related to those in either way? Is dn
Yeah, so
just a subset
yeah,
of L?
yeah, and this is a lot of why it's unsatisfying, really, because we're taking dn out of ln. I mean, well, not take. I mean, because ln, I mean, like we're trying to replicate the beliefs of our given Garabrandt inductor Pn on ln, like the beliefs Pn, which are the ones on day n, we're replicating as they pertain to ln and not otherwise. But it's like, in order to do this, we write down this giant sentence, you know, Qn equals this big table of values. That is, I mean, at least, like, you know, for most possible tables of values, this has to be outside of ln, just because, you know, there's too many. I mean, it's a table of assignments to the sentences of ln, so it's too big to, for all cases, itself be.
Does it need to be outside of L? I
No.
think when you're writing
No,
it,
because, I mean, L could be like the language of Peano arithmetic or some extension of that.
okay,
So the big table of values could be in
you're not
L.
like adding some new, yeah, okay.
Yeah. Yeah, but it's sort of, I mean, it's sort of like by coincidence that it's in. I mean, like, we could do this similar thing without assuming anything about, you know, it might not talk about arithmetic at all. L might be small somehow, and then we could still do this. Yeah, L might be finite, and we could have like some martingale on some finite set of sentences. But then, you know, then we'd have to, then our P wouldn't be just on L, but would have to be on also something else that could support these big table of values sentences.
Norman has a question, by the way.
Yes, thank you. I want to ask, are you generalizing the notion of evidence from deterministic, like originally in the paper, a deductive process is just like a sequence of sets of statements, true statements. So, but now I see like you are using this Qn as a distribution. So, like in the theorem, what is the typeness signature of Dn? And in your construction on the left, is that the same as Qn?
No, so Dn is still, I mean, it's still like an evidence sequence like in the paper. So it's the sequence of, you know, sets of sentences. And I mean, yeah, so what's Qn? I mean, Qn is some function from you know, ln to 0, 1. I mean, we could assume also that it's a probability distribution, so that it's coherent, or propositionally coherent at least.
Do we need to assume that?
Yeah, do we need to? Yeah, I mean, yeah, when we pick our distribution on the space of possible Q2, it has to be supported only on probability distributions, because then we define the probability of phi given Q2 is Q2 of phi for all, for all phi in L, well, here L2, but I guess Ln, because we were going to do this inductively, obviously.
Yeah.
And so if we had any support on Q not a probability distribution, then P would not itself be a probability distribution.
Yeah, right.
So it's unclear what updating would mean then.
Yeah. And so it's like a construction of give me a lot, something that obeys the Garaband induction criterion and is propositionally coherent, specifically on Ln at day n.
Okay.
Then
By the way,
Bayesian logical inductor.
by the way, Julia has asked you to confirm an understanding of type signatures. Could you read that chat message? It's going to be a little bit long to read.
Yeah, let's see. So Q. Yeah, so so Q1 I wouldn't say is a sentence. I would say like quoted Q1 is like the sentence. I mean, yeah, really, I guess this is a sort of. I mean, really, I mean the sentence like, some symbol for Q1 equals, some expression, a big table of values of what Q1 is.
We could also consider just
being like, this function, the assignment from sentences to real numbers. But I mean, basically, it's what this sentence would express. So it's almost the sentence.
Okay, so Qn is this probability distribution over Ln, and then quotes Qn is the sentence given by the price of little L1 in Ln is this, and the price of little L2 in Ln is this, and the price of little L3 in Ln is this, and so on and so on and so on for all of the sentences in Ln.
Yeah, I think what you said is right.
Okay. Oh, the other question I was going to ask, the less short question was about that integral form at the bottom left.
Well, sorry, I should go through the rest of.
Sorry, go ahead.
Julia's. Yeah, the probability. Yeah, I mean, it is a sort of self-knowledge thing. Yeah, I should have made that clearer. That yeah, when we're saying this symbol equals this big table of values, I mean, what I mean, it's like this expression that's like, yeah, I mean, yeah, what symbol equals this big table of values? I guess I mean something like, P, like quoted P of, phi 1 given dn equals P1 and P phi 2 given dn equals P2 and ... So yeah, so it is the self-referential. It's like this table of probabilities is what this computable prior that we're talking about assigns to all of these sentences of L2 or Ln, I guess, after conditioning on the evidence dn. And then this is self-referential because what dn actually is, it is the sequence of conditioning on these sentences for a particular choice of the p's. So you have to define all this with like the diagonal lemma.
Wait, what? I thought you just said that that all of our dn are fairly straightforward subsets of Ln. Is that not true?
Yeah, so you're saying now that we're not actually conditioning on like Qn equals something. but rather we're conditioning on Pn equals something, right?
Well, this
Maybe it works either way.
maybe I said this unclearly. I mean, this is what I meant, but I mean, yeah. What is Qn? I mean, the point is Qn. I mean, it's some particular, it's some probability distribution, some particular probability distribution, and we're going to construct things so that P of phi given Dn is Qn. So by construction, Qn has to be the same as P of phi given Dn. So then when we have to refer to it self-referentially, we might as well just say P of phi given Dn.
But we wouldn't have to necessarily, right? We could just keep talking about Q.
Well, I mean, what actual symbol are we using for Q? Like
if Q is a instance of the logical induction algorithm, then it could be like the written out like algorithm.
yes, except it's not. Q is not exactly like our original P sub n. We had to like round it a little bit.
Well, we could just have an explicit statement of here's the algorithm plus our rounder.
Yeah, but it
is still going to be logically equivalent to
Pn,
but whether we're conditioning, it seems to me that we could condition on an explicit formulation of this rounded version of Q.
Yeah, I mean that sort of is what we're doing, because when we write P, what is P? P is what I constructed here.
Yeah.
So it's like we have this construction involved the rounding and all these things.
Right.
So it's like it is explicitly this description.
It seems to me that you're trying to do something analogous to a fixed point, but using the marginalization language. Is that because, like as you said, you have like P within the marginalized condition, which is what you're trying to construct. I don't fully understand how that works yet, but is that the intuition? Like,
I don't think it's doing like the same work that the like the Brouwer fixed point in the Garbrandt induction algorithm is doing, because like we've sort of already done that work. Like somehow by hypothesis, we had some particular Pn that was a Garbrandt inductor that we're trying to approximate. So there is a fixed point in this sort of diagonal lemma sense, of the self-referential sentence. But I think this is just because, like, if you actually try to do things in first order logic, you end up having to, a lot of normal seeming things end up being self-referential in some form. Like, I mean, like a recursive algorithm, you have to explicitly construct like the Y Combinator to do like some looping construct in first order logic. And so it's sort of just for that reason that I have to use the diagonal lemma.
So the question that I was going to ask earlier was about the integral form at the bottom left still.
Yeah.
So first off, where are you getting, like, what is this integrated over in particular?
Yeah, so this is an integral over like this space of, it's an integral over like the space of assignments to Q2. So
okay.
Yeah, so it's like, I guess we can think of this, I mean, it's like this finite dimensional sort of box of like functions from L 2, 2, 0, 1.
That sounds correct. For in the interest of full disclosure, one of the major reason why I wanted to talk to you about this was pretty much exactly the construction you're laying out here, where I've spent a little bit more time trying to figure out what that has to look like.
Yeah. So
Also, I have a hard out at 12.
yeah. Well, I don't know what time zone you're in, but
I have a hard
Yeah,
out
so-
in under
40
30
seconds.
minutes.
Yeah.
yeah.
In 30 minutes.
Yeah. So
The
what
first
do I think
thing-
about
The
this?
first
I
thing,
mean, yeah, one thing to say about this integral is that, like, when I was saying, like, we make it a discretization, then this becomes like a finite sum.
Right. And
Yeah.
so it seems like maybe the since you're saying, well, the version that's obviously computable, you're not sure about the integral version, but the discrete sum version is obviously maintaining computability.
Yeah.
Right. And so that version, you have a sum there, and what you're summing over is this discretization exactly. And then you just need to make sure that the discretization gets better as n grows quickly enough that you still maintain the logical induction criterion.
Yeah. And yeah, like, how much can you round a logical inductor and have it still be a logical inductor?
Right.
I mean, it's weird because like if you were constructing a logical inductor via like the logical induction algorithm, then like you sort of have like a lot of leeway. You just like you can put aside a pot of money and say like, I'm going to give away this much money on day 1, this much on day 2, this much on day 3, at most, like as an upper bound. And then you just like you round to whatever grid size is small enough, such that like if the market doesn't clear by this amount, you still, which I guess could be a very small grid size if like the traders have like a large Lipschitz constant or like a large like modulus of continuity. So yeah, so if you allow really general traders, then you might not be able to round very much.
yeah, that's one of my worries. The other is that if you don't round at all, for the discrete case, you wind up having to sum up over an uncountable number of sentences, which seems bad.
Yeah, so I mean, yes, you can round it all, and also like if you want to think sort of practically about these things, like Lipschitz traders are like pretty fine. Like every function is like pretty close to a Lipschitz function. And I mean, you can let like the Lipschitz constant grow with time also,
Right.
so that like I think you can satisfy. Yeah, can you satisfy the? No, well, yeah. I mean, basically, I think like in practice, it's like reasonable to satisfy the Garibrandt induction criterion with respect to like a class of like polytime Lipschitz traders. I think that's sort of like a more like realistic class of traders than just like polytime traders with like a more general class of circuits that lets the Lipschitz.
Could you briefly describe what it is makes a trader a Lipschitz trader?
Yeah, so I mean something quantitative rather than really a property, but so a trader on each day has to produce like its trading strategy, which is a function from like market prices to bets, and those are both like.
And that has to be Lipschitz continuous. I see now. Got it.
Yeah.
Lipschitz continuous with respect to some constant.
I mean, it need to be some. I expected it need to be Lipschitz continuous in some topology on the sentences, and that doesn't seem obviously doable to me.
No, well, so yeah, what are we? I mean, we have our space of market prices. Yeah, maybe I should. This here. right, our space of market prices on day n is like 0, 1 to the like ln, if we're only considering
Yeah.
some set ln. And then we give like our trade, which is like reals to the ln. And
Wait.
so
What?
so these, I mean, we can give like a metric in sort of, I mean, we could take, either like some L1 or some L infinity kind of like, right? Because they're tuple, or even like an L2 Euclidean metric, whatever we want, because these are some kind of like tuples of real numbers.
Hold on.
So-
So what?
give
Oh, and the
them
real numbers represent that you're purchasing or selling some number of shares in sentence number whatever.
Yeah.
Okay.
Yeah, and there's, I mean, and there's some, I don't know if you've looked into this at all, but there's these other equivalent forms, like where I mean, instead of the number of shares, you might give like the price of sentences you buy or sell, or you might give like some effective probabilities that are like the probabilities that we interpret you as having if we think of you as maximizing logarithmic expected utility. So we might have like other kinds of things that would give different metrics if you did just some, LP kind of
Yes,
construction.
okay.
But
Yeah.
are like some other function formally, like maybe some function from probability distributions. But
Yeah,
like
okay,
any
so
of
this-
these,
Okay, so yeah,
we
it's
can give some
not
metric that are-
just from sentences to price, sentences to how much to volumes, to sale volumes. It's from specifically if the prices for these things are this, then do that.
Well, I mean that's like the interpretation of like it's like we have some function from prices to volumes, but the way we use it in the Garbrand deduction criterion is we interpret it as what the trader does given these prices.
Thinking about it more, I'm not at all sure that like some LN norm is, or sorry, some LP norm is what you want, because that would say something like being arbitrarily close to certain, or being not quite certain is as close to being completely certain as like being 49% certain is to being exactly indifferent between two options. I was thinking actually the form that I wrote down for the bottom left integral, which I still haven't gotten to talk about. I mean, what I've realized is you probably can't condition on an event of probability 0. So the primitive you should be looking for there is that you have some statistical distance between some statistical difference between your assigned Q and what tomorrow's Q really would be. And you have some, I mean, I think I've written down as possible candidates the KL divergence, the symmetrized KL divergence, that general sort of thing, such that you're all, such that one coordinates that are 0 or 1 really are very far away from things.
Well, so yeah, what do I think about? I mean, so I think the Fisher distance, I guess, yeah, like geodesics are finite in the Fisher distance. So, well, I don't know if the Fisher, I mean, yeah, what am I trying to say here? I mean, so somehow we want this discretization to be finite. So we don't want to say like, every step in log odd space, we introduce another point. I mean, I think it maybe doesn't matter that much if we're willing to like condition on like an infinite set of sentences dn. I think like, yeah, possibly you could just condition on an infinite set of sentences dn, but still have like this whole construction be computable because you like approximate it. But I think we can assume the traders are such that like, I mean, because the traders have to have some like trading strategy specifying like what they would do at the extreme. And so, in this like Weierstrass approximation sense, there has to be yeah, I don't know. Yeah, I mean, what am I trying to say, broad? Like, I think you can make this work with some sort of. I mean, you can definitely like make this work with some sort of like Lipschitz hypothesis on the traders, but there's a question like what the most natural kind of metric to state the Lipschitz hypothesis with respect to is, or like maybe something slightly different than a Lipschitz constraint. And yeah, I don't know. I mean, probably. Yeah, I mean, yeah, statistical distances are going to be more natural than these. Well, I mean, like L1 is just like variation distance, which is like a very natural probabilistic thing, and then like something like a Fisher distance or a KL distance is also natural. Yeah, like in a KL distance, like if geodesic length will be infinite.
Yes, and I claim that we should want for it to be.
Yeah, I mean, for some purposes, it makes sense to think of the geodesic length as infinite. Like somehow, like it's like, I mean, evidentially, it's like an infinite sequence of updates of equal evidential magnitude. Yeah, I mean, so, I mean, maybe I should just ask you more like how you're seeing that. I mean, I guess you can say like it should be reasonable for a trader to specify like an infinite sequence of like qualitatively different behaviors along this infinite geodesic.
Yeah, I would say that.
Yeah. What do I?
I mean that matches up to. It at least passes a smell check of as you become increasingly ridiculously certain of this proposition or of its negation, that maybe causes you to do some things very differently.
Yeah. I mean, in the computable context, like the trader has to give some like finite algorithmic object that is its trading strategy. So, I mean, we could have like we might have like a sign or something where we oscillate if we allow that in our. Well, yeah, I mean, the thing is, it doesn't actually matter if we have like a rich enough set of traders, because we're going to have these like non-dogmatism traders that like prevent anything from actually being too close to 0 or 1 unless it's already been observed in the deductive process. So I mean, we can consider like markets without like we can consider like weaker
markets in an open interval.
Well, I mean, the thing is, we want the Brouwer fixed point to actually work. So, I mean, the reason the Brouwer fixed point actually works, I mean, either because
you're compact,
we're really working on a compact space. We actually have.
Oh wait, does using statistical break, using like KL divergence break that then? Because now under that metric you're no longer compact, like specifically.
Yeah, that's the thing. I mean, like either we complete it by adding these endpoints, or I mean, instead of the compactness, we could have, which is essentially the same practically. We say that like outside of some compact region, there's like some inward pointing kind of condition, which there's different forms this inward pointing kind of condition could take. And if we assume enough traders, we do have in practice this inward pointing condition, because we have these like dogmatism traders that force probabilities like back into the middle.
Okay. Wait, so then why do we want a fixed point? Like, where's Brewer's fixed point getting used here? What is the map on 0, 1 to the ln that we care about so much?
Well, I mean, it's used, right? I mean, this theorem about Bayesianizing Gariband induction. I mean, Bayesianizing like a given Garabrandt inductor. So the actual use of Brauer's fixed-point theorem is the existence of the Garabrandt inductor, which here I'm taking as hypothesis. But I mean, in general, if we have existence when we have this when we can do this Brouwer argument. But yeah, like what's an example of like a market where we couldn't do a Brouwer argument? Okay, actually the thing is, really you can't just say we're going to work in the interior of this space, because some things do get decided by the evidence sequence. And so then you actually have to say, like, what would I do on the boundary? Because you might be constrained to the boundary because something might be learned by the evidence sequence.
That's
so probably
true, but now I'm thinking about this, and don't we wind up with, isn't that just a meter set? Like we have an integral that's not going to be, we have an integral, we have some measure that's not atomic. I'm going to put in a guess. And so
our measure
here
is atomic. If we do the discretization thing, it's purely atomic.
Sorry, could you repeat that?
If we're doing this, like if this probability distribution is supported on some discrete set of Q2, then the measure is atomic. It's only atoms.
Discrete set of. Does that ever happen? Because that would be saying that our logical inductor has non-zero credence precisely for a handful of possible Qi.
Yeah, I mean it's like you know that what my beliefs are tomorrow will be in this discrete countable set. And in fact, that's right. What your beliefs are tomorrow will be in this discrete countable set by construction.
Huh.
But then, like you don't meaningfully know this because it's not itself like in L2. So like none of the traders are really looking at it. But you in this like non-introspectable way, formally know it.
Okay. Do other people have questions? I don't want to monopolize the time here.
Yeah, I think that your discussion is helpful for my understanding.
Of course.
Yeah, what Paula and I had been talking about was mainly like, how can we make sure this integral version works? And so what I'm updating now towards, well, the discretized version actually makes a lot of sense and might be the simpler way to go to make it like obviously computable.
Yeah. Yeah, I think that it is. Yeah, I guess I didn't think about this too much when preparing this talk, but I think the integral version also works, and like, no, not so confidently. And if you're interested in whether it works, you can try to make it work. But yeah, what I had in mind is like the simple argument is just you construct it so that a priori by construction it lives in this discrete space.
Right. The integral version is in some sense simpler in that it could tell the story where we take an arbitrary positionally coherent inductor and then we don't modify the prices at all. We don't modify the small prices at all. We just turn it into a Bayesian inductor.
Yeah, that is nice.
It's like the more
sort
natural
of
form to me.
unsatisfying that we have to modify it at all when it's given already.
Do we though?
What's that?
Do we though? Except we have to modify this in some way, do we though?
For the discretized version.
Yeah, for the discretized version, yeah, could we come up with some trick where we like construct the discretization so that it happens to contain the true value? Yeah, we probably could. Yeah, that's really an obnoxious construction from the point of view. But yeah, I bet we could do that. We just like in the self-referential thing,
We can't
we
see
like
the
define our discrete set so that it happens to contain, you know, P of phi n given dn.
We can't see
our
we can't
original
see
Pn.
at all.
What's that?
We can't see the whiteboard. You're writing lots of things and we can't see them.
Yeah, so sorry. I was gesturing rather than writing, but yeah, I have to plug in my laptop because I don't know why it ran out of charge so quickly. I thought I had charged it, but yeah, and now it's sort of far from the. Well, yeah, sorry, I didn't realize I'd have to plug it in, but yeah, what was I? Yeah, it's like we constructed. Yeah, like we could self-referentially define P so that like, yeah, like this random variable Qn has in its like discrete support Pn itself. Yeah, I shouldn't have called this Pn and P. This is sort of confusing, but hopefully you don't get too confused. I mean, Pn is like a given logical inductor, and then P is the probability distribution we're constructing from it, and then like Q is like, yeah, Qn is this other family of probability distributions, and also like, I mean Q, I mean it's you know intentional rather than purely extensional, because then I quote Q to mean, you know, P of phi given dn, or whatever other intentional like form of expression you want to use for Q in the language of the logical inductor itself.
Okay. Norman again?
Sorry, what's that? Oh, yeah.
I have a question. So after all this, I think I understand better the construction, but I still don't understand why we're doing this. Because like if your dn is actually some table, and you're updating, you're defining a notion of marginalizing on that to produce your logical inductor, then I just don't see what this amounts to. Like what's good about this? Because like yeah, like the dn. So where's that dn, the table, supposed to come from? Is it like recursive?
Yeah, it's like dn is just the sentence, yeah, with this table that we like constructed inductively in this algorithm. We constructed it from the original logical inductor. We haven't given like a construction that avoids, say, our fixed point or something. So I mean, I think this construction is very disappointing. I think mostly it's like saying you can dress up a logical inductor as a Bayesian induction process, but it's just dressing it up. It's not really giving us more insight. And so, I mean, what I'm interested here, I mean, like, I think if you could give somehow a more meaningful construction, and in particular, here, like, the belief sequence we get by conditioning P on this particular evidence sequence dn is a reasonable sequence. And we can do a little better if we can condition P on dn and also like a few more facts that are in ln. Then, like, you know, we have some like growing additional thing. then those beliefs are like still reasonable. Like they'll satisfy like a modified logical inductor criterion for like, this like D prime that's like conditioning on a bit more. So like I can spell that out a bit more if you want, but I mean, what I'm getting at with that, it's like it's like I mean, a Bayesian, we'd like to be able to trust that if we condition on like a big space of sentences, then you still have reasonable beliefs. Actually, sorry, what I said is false. We can't just condition on some extra things. We have to like do something self-referential. Yeah, how does this work? Because we have this problem that I raised of like we can condition on something explicitly misleading. Yeah, like we don't want to condition a Bayesian on some sentence. We want, I mean, and this is how you really do things in the continuous case also. We want to take like the disintegration of measure with respect to some sigma algebra. So it's not just this sentence is true, it's like, this sigma algebra represents some like state of information. And like, so I mean, you can say, we tell you the sentence, but we also have to, if we didn't tell you the sentence, you have to be conditioning on the fact that we refrained from telling you the sentence. So maybe by construction, I only tell you true sentences, but then it's meaningful when I omit telling you a sentence, even though that doesn't tell you whether it's true or false. Because it's like, really, you don't just have like this event of, you condition on the sentence and the sentence is true. It's like you have the sigma algebra of like, there's the event I tell you this sentence, and there's the event I don't tell you the sentence. In some of the worlds where I don't tell you the sentence is still true, unless it happens to be the case that we know a priori that I tell you the sentence if and only if it's true. But in that case, like it's like you're either conditioning on it or you're conditioning on the negation, or like we have this modified set.
Sorry, is the I you're saying here referring to DN?
Yeah, like the I is like the evidence, basically.
What,
Where?
isn't it what you read as D tilde in? Like the I is like the deductive process, like.
Yeah. Let's say it's detailed to N. Well, I mean, we can consider either a situation. We consider like just like a Gary-Grant inductor and like what, what do I mean? I mean, the thing is, like, the Gary-Grant inductor, like, we really do just tell them these sentences, and they, like, figure that out. They figure out what to do with that. Yeah. I mean, we can say it's like we have this event of, like, I presented this sentence, but
there's not that explicit event.
Yeah, it's just like the algorithm works out when we show them the sequence of sentences. We're not really thinking about this like sigma algebra of like, here's all the different sets of sentences we could have presented you with. And also like it sort of doesn't like there isn't really the other possibility in some sense. Like I mean, there is, if in this kind of like tree picture of like empirical uncertainty branching, but like a lot of the things we think about Gary-Grant induction, we just think about like it's like, well, you come to know these like true mathematical statements. But then like this Bayesian idea of the evidence sequence, that should be like a filtration of sigma algebras.
In the short amount of time we have left, maybe
words, but yeah, also, yeah, we have very little time.
Maybe we should discuss the like showing that these things exist. Like you've written conditions on the board, but we would like to know that such a thing actually exists as well, right? So in particular, showing that we can chain the Markov kernels together, but showing that we can balance that last equation, right?
Yeah. Yeah, so why can we balance this equation?
How about if? I don't see anywhere in the current picture where the DNs like the sentences QN sentences are connected to the original deductive process. Did I miss it?
No, I did gloss over this also. Yeah. Yeah, because I've sort of like I've written this like sort of very big sentence that's like not going to be in ln, but like yeah, maybe this does deserve more. I mean, like eventually, well, I mean, one thing we could just say like, I mean, the simple thing is like we could just say this is a new sentence. We actually are extending L, and then I can really do whatever I want. But I mean, if we like this idea that that like we're L is very expressive, let's write a sentence in our existing language L. I mean, why can't the sentence just be something like this? Then we need it to be the case. Eventually, it is going to be in some ln, and like we want the Gary-Grant inductor to believe it as soon as it enters ln. We want it to be like evidently true. So yeah, I mean we can arrange our original Gary-Grant inductor such that this holds, because I mean like
No, you're saying you can arrange the inductor, but isn't the deductive process fixed? We're not supposed to be able to change the detail that end, right?
yeah. So what am I actually? Yeah, like I guess I'm changing like very slightly the deductive process. Like I want it to be the case that like as soon as the sentence enters like the evidence sequence, or sorry, enters ln, then it's already decided by the deductive process. So like I could just say like like I write this like I can make this sentence like trivially long by having like a bunch of like and 1 equals 1 and 1 equals 1 and 1 equals 1, etc., or something like that. And I can just say like, well, let's take this like very minimal constraint on our original deductive process that like any sentence that's like something like easy to check, like you can just like calculate this plus like a bunch of and 1 equals 1 at the end to give you a lot of time to check it, becomes like determined by the deductive process as soon as it enters ln. So yeah, so this is taking some assumption on the deductive process, which I didn't make very explicit, but I want to say like it's very easy to also have this property.
I'm lost. Why are you adding this property?
Because I mean the point is this is some actual sentence.
Yeah.
Like I've defined P on L1, and then I defined it on like all the sentences of this type. And then I extended it to L2. And then I defined it all the sentences of this type for like, D3. And then I define a L4 or L3, and then I do it on all the sentences of this type for D4. But eventually these long sentences are going to themselves be part of some ln, and I need that not to be inconsistent.
Yeah, okay.
So yeah, so it's like I'm gonna make this become certain at some stage. So then later, when we get there in L, we need L to we need the other definition to agree that it's certain already.
Yep, that seems important. Okay.
Sorry, I know it's almost time. So, Paul, do you have anything else to say? Like, I just Yeah.
Yeah, I'm still left very unclear as to what's going on with the f of dn tilde. I don't know if you explained that at some point in the process and I just missed that, but I'm looking at the thing about the untrollable mathematician again and trying to figure out how this connects up to that, and I don't see how any of that connects up to conditioning on what you observe rather than what observations happen. Maybe this is too long for the last few minutes.
Yeah. I think I can. Yeah, this. Yeah, what do I? Yeah. So this isn't written very clearly, I guess, but yeah. So dn tilde, I mean, is like the kind of evidence sequence in the original like logical induction paper, where it's like the sequence of like sets of. Yeah, how is it that is it just sets of sentences, or is it's like sets of like propositional coherence conditions? I don't know, whatever it is. But then like dn, I want to be, I don't know if you know filtration from probability theory. It's not just like a sequence of events that are nested, but it's like a sequence of like sigma algebras that refine each other.
Okay.
And then yeah, why am I saying that? I mean, I don't know, like this just uses like these particular events. Well, I mean, if they're finite, I mean, in general, like we need the filtration to talk about what this means, which we would want to do if in the continuous world where we have this integral. But like, I don't know, like we could just say like, you know, we have the event and then its complement, but yeah, I mean, I'm trying to, I don't know, I'm trying to like dress it up as like a reasonable Bayesian, even though I think it is unsatisfying in a bunch of ways. So what I'm saying here, it's like we have this kind of like branching tree of a filtration, and like all these paths are like sort of as reasonable as I can make them. It's like I'm saying not just you condition on like dn, but like for all the possible values of dn, you can condition on that, and you get like, you know, you get p of phi given like this like qn equals such and such sentence is actually equal to qn for like all the possible like qn tables, whether that's like some discrete or continuous set. I don't know how well that.
I don't know if this is relevant, but I think I get the sense that in the paper it is the intuition. There's some at some point it's mentioned that the intuition is that the logical inductor races ahead of the deductive process itself.
Yeah.
So if we if we marginalize on this dn that or new dn, I think it shouldn't be a function of d tilde n, but instead it should be like taking maybe like the only way that it could have worked maybe is like, I don't know, like taking some combination of d tilde n, not just the like the one on that day.
Well, it's like we are sort of putting something more in dn that wasn't in dn tilde, right? I mean, like the point is dn, I mean, it is like this big sentence giving this like big table of beliefs. So it's like whatever the logical inductor like raced ahead, and came to know about L, about the sentences of L, it's like everything that it knew by day n, we're like putting into this sentence dn. So dn is like, in turn racing ahead and capturing everything that tn knows.
Here's how I would think of it. I realize Paul has to
I need
go.
to head out like 5 minutes ago, but please go ahead.
Yeah, sorry.
I understand this.
I'm like, philosophically, you were like, okay, Bayes' law, or like, sorry, Bayesian updating is problematic because the Dutch book assumes that you have to be able to look ahead and say how you would update hypothetically on the given information.
Okay.
And that's like the D tilde is like, well, the D tilde is the information that we don't actually know how we would update on yet. And then it's saying, well, there's one case where we can justify this completely, which is the case where we treat the observation just as our whole mental state, that we observe our new epistemic state and we believe it. And there we can just trivially say, well, what we would believe observing our whole mental state is just that mental state. And that's the DN.
Yeah, I think that's a good way to think about that. And it's sort of like, it gives a more general idea that like if we're willing to extend the language, we can sort of do this like very broadly for like any sequence of like coherent beliefs satisfying like some martingale condition. We can like match all these branches of what we believe in these different like what do I mean? Like satisfying a martingale condition. Like basically we have some probability space that might be bigger than like the space that you have beliefs about, but it's like the space of like how we like from the outside see your beliefs randomly moving. If we would describe them as a martingale, we can then like concretize that martingale with some auxiliary variable that is like this your whole mental state variable. And so it's like we can make anything that satisfies like these like weaker Dutch book properties that are like these martingale properties, but not these stronger ones that assume you anticipate things. Like, it might be that like, I signed 50% to some proposition today, and tomorrow I'm either going to sign probability 0 or 1 with some objective, or at least like some like third person 50% on each of those. So I'm a martingale from this third person perspective. But I don't have myself some proposition I can state that is like the evidence that I would get. Like we can still make me into, like we can add this auxiliary, like my mental state, and make me into some evidence that way. But sort of very just formally, we just do it by construction. And then here we have to do additionally, most of this work is just like to make martingale, where some of it is like, because we want this to actually be a sentence in the language, we have to deal with these self-referential things rather than just having it be some new sentence, including the thing which I glossed over as you pointed out about like, well, how do we make sure that this does have probability 1 when it itself becomes part of L?
All right, maybe we should close it there.
Thanks.
Yeah, thanks.
Yeah, I think that sounds good. Yeah, you can. I guess people can email me with questions if you want, or I don't know, like any follow up. Just I don't know. Abram can. What's the? I don't know. Yeah, what should I end this with? I don't know. I think that's that sounds good. Yeah.
All right. Take care, everyone. I'll post the video soon.